In section 11.1, I'm going to discuss some of the history and concepts concerning Newton's law of universal gravitation. Isaac Newton is credited with the first great unification of science, where he joined together previously described phenomena of gravity on Earth and known astronomical behaviors. And on this slide, I'm going to show you some of the observations that Isaac Newton would have been aware of at the time. He knew that on Earth there seems to be some force that pulls downwards, causes dropped objects to accelerate downwards, and he knew that objects moving in circular path required a force pulling in the centripetal direction to cause that circular motion. In the heavens outside of Earth, he would have been aware that the moon orbits the Earth in a roughly circular path, the Earth is orbiting the sun in a roughly circular path, and that there are some other objects that also orbit the sun in roughly circular paths. Also, he would have been aware that Jupiter and Saturn seem to have moons that orbited them as well. And he would have been aware that there's some patterns in the orbits of the planets that were outlined by Johannes Kepler, known as Kepler's laws, that we'll cover in 11.4. And so Isaac Newton came along and he said, well, if accelerations require forces and circular motion requires forces, the force that causes objects to have weight on Earth is the same force that keeps planets in the orbit. He joined together the effect of gravity on Earth with the effect of gravity in the outer space. This blew people's minds at the time. Isaac Newton is credited with being the first to mathematically describe the strength of gravity between two objects. And this is what's known as the law of universal gravitation. Newton stated that all objects attract all other objects with a force called gravity, and we call that force weight. The word universal is to reflect the fact that all objects with mass, all objects in the entire universe, anything with mass attracts anything else with mass everywhere. And Newton described this with an equation that we call this law of universal gravitation. Here it is. Any two objects with mass, and here m1 and m2 are representing the mass, separated by a distance r, will attract each other with the force described in this law. If we're using this law to describe the force between an object and another orbiting object, r can mean radius, but generally r stands for the distance between the centers of the objects. 120 kilogram person is standing on Earth's surface. What force does this person exert on the Earth? A person exerts a force on the Earth? Well, if a person is standing on Earth's surface, they are a certain distance away from Earth's center, because we always measure r from center to center. So that's the distance to Earth. It's the Earth's radius. And the person is pulled downwards with a force equal to their weight. And 120 kilograms weighs 1,200 newtons. Well, Newton's third law of motion, the action-reaction law, says that if the Earth pulls down on the person is going to pull up on the Earth with the exact same force. It's important that we understand every object, including a person, would exert a gravitational force on any other object, including the Earth. So what did Newton actually say about gravity? Well, in 1687, he came out with his most famous work called Principia, and he wrote that the force of attraction between any two bodies is proportional to the product of their masses. So it's the product, it's not just one mass, it depends on both masses. And it's inversely proportional, which means that it gets smaller when distance increases, to the square of the distance between their centers. It isn't just inversely proportional, it's inversely proportional to the square. It's what we know is what we call an inverse square relationship. And when we combine these two ideas, we know that the force is some constant, and Newton did not know what that constant was. He just described the proportionality. Finding that constant was important. That constant is very, very difficult to do because gravity is very, very, very weak. We call that some constant the gravitational constant, and we use capital letter G to represent it. It's very important that we understand that big G, the gravitational constant, is not the same as little g. They are very different things. Big G, gravitational constant, is a fundamental constant of nature. It's the same everywhere in the universe. Where little g, gravitational acceleration, depends on the location. It's different on the moon than it is on the Earth. And in 1798, English physicist Henry Cavendish was the first one to accurately measure G. He measured it within 1% of its currently accepted value. And here's how he did it. He took two big cannonballs in this diagram labeled capital M, and then he suspended from a wire two smaller cannonballs joined by a rod. He then twisted the wire, causing it to want to go back to where it was, but it didn't go back to where it was because the tiny red balls were attracted by the large cannonballs shown in gray. And because this is such a sensitive setup, he was able to accurately and precisely measure the value of G. Today, we're confident that we've precisely measured G, at least to a few digits, but G is very, very small. Look at all those zeros before the first non-zero digit. Typically, we'll write it in scientific notation as 6.67 times 10 to the negative 11th. What about the units? Well, if we take the law of universal gravitation, algebraically solve it for G, we can then decide what the units for G should be. So taking the typical unit for mass, the Newton, multiplying it by our units for distance, because r is a distance, squared, and then dividing kilograms and kilograms. That gives us kilograms squared in the denominator. These are the typical units that you would see for G. However, positive physics does not offer this as an available answer choice when it asks you for the value of G. So it offers it in more basic units. A Newton, which is the unit for force. Remember, force is mass times acceleration. So a Newton is really just a shortcut way to write this. So if I write this expression where I see newtons, kilogram meter per second squared, times meters squared, divided by kilograms squared, several of these units are going to cancel out. Kilograms will somewhat cancel out. And what's left over, I have meters times meters squared. That gives me meters cubed. In the denominator, I'm going to still have kilograms. Kilograms did not completely cancel out. And I'm going to have divided by seconds squared. So that goes in the denominator. These are the units that positive physics will accept for the units for G. Henry Cavendish's experiment. Henry Cavendish's experiment is known as the weighing the Earth experiment. Now, Cavendish did not weigh the Earth. What he did was he measured G, big G, and that allowed us to calculate the mass of the Earth. Well, here's how we did that. We knew the radius of the Earth. We've known that for a long, long time, and we're able to measure very accurately little g, the gravitational acceleration at the surface of the Earth. And if we consider an object of mass m, and it doesn't really matter what that mass is, you'll see why in a second. The force acting on that mass is equal to m times g. That's the weight of the object. And Newton came along and said, well, that force is big G times the mass of that object times the mass of the second object, in this case it's Earth, divided by the distance between the Earth and the object. And in this case, it's going to be the radius of the Earth, because we measure distances from the centers of the object. The mass of the object is going to cancel out, and from the remaining 1, 2, 3, 4 variables, we can rearrange this for the mass of the Earth. The mass of the Earth will be little g, gravitational acceleration, times the radius of the Earth squared, divided by big G. And if we take all of these values using standard units, we end up getting an accurate calculation for the mass of the Earth. The Earth is 5.96 times 10 to the 24th kilograms. This is how we know the mass of the Earth. Having an accurate measurement for the mass of the Earth had some important consequences for our understanding of geology and what's going on under the Earth's surface. We could easily calculate the volume of the Earth. The Earth is roughly a sphere, and the volume of a sphere is given by 4/3 pi r cubed. We know the radius of the Earth is 6.37 million. 10 to the 6th is a million meters. And this will yield 1.08 times 10 to the 21st cubic meters. And if we know the volume of the Earth and the mass of the Earth, we could calculate the average density for the Earth, taking its entire mass and dividing by its entire volume. Once Cavendish had figured out the mass as 5.96 times 10 to the 24th kilograms, I can divide that by the volume of the Earth. This will give us the average density of the Earth. It's 5,500 kilograms per cubic meter, or in the units that geologists like using, that's 5.5 grams per every cubic centimeter. Now, if you go out and you find a rock on Earth's crust, then you're going to see and measure its density. You're going to find its density is about 2.6 to 3 grams per cubic centimeter. But from Cavendish's calculation, the Earth has an average density of 5.5 grams per cubic centimeter. So the Earth on average is way denser than the material that we find on Earth's crust. So what does that say about the structure of the Earth? Well, it says that inside the Earth, underneath the crust, that Earth has to be a lot denser than the crust. And that's how we have come to understand that the Earth's core is much, much denser than its crust. Newton's law of universal gravitation gives us what we refer to as our classical view of gravity, that two objects attract each other, and there's really no explanation of why. Einstein had to come along and correct it. So here are some problems or limitations for Newton's law of gravity. The orbit of Mercury is an elliptical path around the sun, and that ellipse seems to rotate as time goes on. Now, Newton's law predicted that that would happen, but the astronomers had observed that the precession of Mercury around the sun is much faster than Newton's prediction. Einstein came along and he corrected this idea with his theory of general relativity. And in his theory of general relativity, Einstein predicted this effect, gravitational lensing, that gravity would seem to bend light. And we have actually observed this. What you see in the lower left of the screen is an animation of what we've observed when a galaxy passes behind what we believe a hole. You can see that when the galaxy passes behind the black hole, it seems to distort the image of the galaxy. And the reason that it's doing that is gravity is bending light. And that's how a lens, a regular lens works. It bends the light passing through it. So was Newton's law of gravity wrong? No, it wasn't. It was just incomplete. It does a great job of making very accurate predictions for the orbit of planets, for what gravity does to regular objects, but it fails to make accurate predictions under very strong gravitational fields, and that's where Einstein had to come in and make a more accurate theory with his theory of general relativity.